Why the video froze on me? That was weird. So we're talking about Pascal's law, which we've stated here. We're going to apply a force to do a certain amount of work on this. So the distance is going to move is about 7 lines on this paper. And you can see I'm lining up the big syringe with one line. And when I do the work, it moves this syringe about half a line, which tells you something about the area of these things. All right, and it's based on this. We're doing a certain amount of work and using that to move this piston around. So if you wanted to remote control something, this is a possible way of doing it. Now this is fairly easy to do. You don't have to apply very much force here, but if I want to move the other syringe, I have to apply a fair bit. I'm going to have to do it like this. It takes a fair amount to make it move. And that's because the area is so much larger, so I also have to increase the force. All right. So, all this is aquarium tubing and cattle syringes. So it's a fairly nice thing to make and cheap. And, some people use it for, like, if you need to remote control something, but you can't use electricity, you can run a hydraulic line. That's how hydraulic systems work. That's the principle, is doing some work on one end of the thing cause some work to happen on the other end. All right, so I want to get into fluids because we're really getting into fluids here. So let's talk about fluid flow. All right. So you've held your thumb over a hose, I hope. You've had a garden hose and you've covered the hose up with your thumb. And what you notice is if you close the area off, the fluid comes out faster. Right? And so there's a principle there that's going on. The idea is that we have some pipe, and then we're going to make the pipe larger, and maybe we're also going to lift it up. So we're going to follow a chunk of liquid that is currently down here. There's a chunk. And so this chunk has mass, which is density times volume, and we'll make that big V for volume, and it has a velocity. All right. So it also has kinetic energy. 1/2 mv squared. So we can also put it in here, and we're going to measure height here. So it could have some potential energy as well. Would be mgh, which is rho g v h. Okay. So let's say we do some work to move this. The work that we do to move this little chunk of fluid is going to result in it coming up here somewhere. And based on our Pascal's law, based on finding continuity, then we know that the area times delta x here, how far we move it. So it moves from what's going to happen is it's going to push other fluid up out of the way. But what this means is it can move, this chunk will move a fair bit, but this big chunk gets standing up here in the way. It doesn't move as much because it's smaller. And we can put in delta t. So continuity says that the area times the velocity is a constant. That's one of the things we're doing is these are conservation laws in a sense. We're saying here the mass is conserved, and here we're saying that the energy is conserved as long as the fluid's static. And now we're going to say that the energy is conserved when the fluid flows. So here we're saying that not only is the mass constant, but the rate at which the mass flows through the pipe is constant. So we can talk about the energy that's in these points, right? And so at a particular point, let's go through another sheet of paper here. So the energy, well, there's three forms of it. There's the work that we do, which is F delta X, which is the pressure times the area times delta X, which is the pressure times the volume. Okay. Then there is the kinetic energy, which is 1/2 the mass times the velocity squared, which is 1/2 the density times the velocity squared times the volume. And then there is the potential energy, which is mass times g times height, which is density times g times height times volume. Right. And so these things, you understand the kinetic and the potential. The work here is, well, for this chunk of water, it might be us pushing it through, but for other chunks of water, it's the water behind it and the water in front pushing it. All right, so what this work is really the internal energy of the fluid. And so if we were to write this in terms, we would have 1/2 density times velocity squared times volume plus density times g times height times volume, plus now we'd have this internal energy, pressure times volume. But let's just divide everything by volume. And this leads us to what's called Bernoulli's equation, which is that the pressure plus 1/2 rho v squared, where this is velocity, plus rho g h is a constant. So what we're doing is we're identifying this is the kinetic energy, this is the gravitational energy, and this is the internal energy per unit volume. So these are energy densities. And so if the energy is conserved, so is the energy density. Now let's talk about how to deal with that in a problem. We're going to have a jug of water, and the water is going to leak out the bottom. Right, so let's put in a jug. Let's put in some water. Let's put in some height. Say 1 meter, a big jug of water, a 5-gallon bucket of water, let's say. And we're going to put a hole here. And so this hole, when we open it, the water is going to flow out. It's going to have some speed v. And that's what we want to know, is how fast is it flowing out. So to do that, we need to figure out what's going on everywhere else in the system. And what we're going to say is that this hole is very small compared to this hole. So as fluid flows out, not that much can flow out. So we're going to talk about the energy density here. And then we're going to talk about the energy density here. And those two energy densities have to be equal. That's the energy conservation bit. So here, what we have is 1/2 rho v squared plus rho gh plus pressure. So the pressure here is 1 atmosphere, because this is just a container that's open to the air. So this is 10 to the 5 Pascal. Right? So here, the velocity is really 0. It's really, really, really close to 0. We're going to pretend it's absolutely 0. Obviously, this layer has to move down as it drains out, but it's slow compared to the speed of the water flowing out here. So we'll have this term goes to 0, and our energy density is 10 to the 5 Pascal plus, and then our rho GH. This is water, so 1,000 kilograms per meter cubed times 9.8 meters per second squared times 1 meter. So this is 9,800, so we'll round this to 10 to the 4 Pascal. And so we can put in 1.013. So the energy density is about 1.113 times 10 to the 5. Anyway, the point is we can figure this out. Now, what about the energy density at the bottom? Well, H is 0 here. So when we write that out, that's going to be 1/2 rho v squared. V is not known, so we leave it alone. Plus rho gh, but this goes to 0. Plus, and now we have plus the pressure. But the pressure here, if this is open, outside of this pipe, it's 1 atmosphere. It's the same pressure. And so these things have to be equal. So if we just write it out longhand, so we'll have 1/2 rho v squared plus rho gh plus p. And so this is at the surface. That has to equal 1/2 rho v squared plus rho gh plus p. But this has to be at the hole. And so the pressures will go away because they're 1 atmosphere, they cancel out. And the height will be 0 at the hole, and the velocity will be 0 at the surface. And so what we're left with is rho gh for the surface equals 1/2 rho v squared for the hole. Well, the densities go away. It's the same fluid. And surprisingly, you get this formula. V is square root of 2gh, which is exactly what you would get if you just dropped the object from the top of the water down. So, I mean, this is going to be 2 times 9.8 times 1 meter, so it's going to be square root of 19.6. So it's going to be about 4.2 meters per second. You get the same result. The speed of the water going out the hole is the speed of the water falling from the surface to the hole, which is what we kind of expect. The water has to fall from the surface of the water to the hole. Now, obviously, it doesn't do it all at once. It pushes water out. So this is how we try to do problems. How we try to do fluid flow problems is we look at the energy density, and it's conserved. And so we look at the energy at one location in the fluid and the energy at another location. So I'm going to stop this video, and I think this is it. I think this is all you need. If there's more need, I'll do another video because there is a story I want to tell on this stuff, but I think this is the gist of it. What you need out of all of this is Bernoulli's equation is that this stuff is constant. And so you can call this the mechanical energy density. E over V mechanical is the pressure plus 1/2 rho V squared plus rho GH. All right. The potential energy, the kinetic energy, and the internal energy is the total energy over the volume. All right. So you need this. You need Pascal's law and the continuity law. So you're also going to need something that looks like A1 V1 is A2 V2. Right. So you'll need the continuity law. And you'll need the original. Right. Note that this is Bernoulli's law if the fluid doesn't flow. All right. You have at one location, you have H is 0. There's no fluid flow, so the velocity is 0. And then you just have the internal energies and potential energy. So these are the things that you need. So I'm going to stop that and upload these so you can look at them. And if you have questions, please email me and we'll go over stuff. I probably do have one more thing to show, but I don't know how I want to get it done. So let me leave you with this. Go to your faucet. Actually, let me get a sheet of paper out here. Or on the other side of this. Go to your faucet. So your faucet looks like this. Yeah, so go to the sink, look at your faucet. There's your faucet. When you turn the water on, note that the water starts up here at this thickness, and then it quickly narrows out, and then eventually it's droplets. So if you turn it on fast enough, it will hit the sink. But if you narrow the stream, if you adjust the faucet, you'll eventually see that the stream narrows. And what's happening here is, let's look at this chunk of water, and it has V1. Then as it gets down here, it'll have V2 is V1 plus V2 squared is V1 squared plus 2GH. Right. So the continuity up here says A1 V1 is some number, but that has to match A2 V2 here. So as it speeds up, the cross-sectional area has to narrow. And eventually, you get to a point where you see these droplets is the force that's holding the stream is weaker than the force that forms it in, the surface area forces that hold it as a sphere. So it turns into a little sphere. So try this. Go to your kitchen sink, go to the bathroom sink, turn the water on until it's a very slow drain. You'll see that it curves like that. All right, that's where I'm going to stop.